Grade 12 Physics, Special Relativity, Note 6. Here we're going to do some additional thought experiments to see how special relativity affects things around us. Here we have three circles drawn. Say this is a really big record player, and it can travel or it can spin near the speed of light. On the record player, we're going to add spots A and B. And basically what's going to happen is we're going to want to see how an ant is going to crawl from A to B. First of all, on the first record player, let's add some dots from the middle towards the outside and see how the speed changes between them. Near the middle, the record isn't spinning that quick, so we can show that with a smaller velocity, but as we move to the outside, the velocity gets quicker and quicker and quicker. So how is that going to affect if we have a meter stick? So if I'm going to pick up a meter stick and put it near the center versus the outside, near the center it's going to look pretty normal. It's going to be that length. But as I start moving to the outside, length contraction is going to occur. It's going to get smaller and smaller and smaller. So remember, there's still meter sticks, but because of length contraction and because it's faster near the edge, they're going to look smaller. So let's say the ant has a choice of two paths. It's going to crawl from A to B and it wants to do it in the shortest length. Normally that would be a straight line. If I lay down some meter sticks on that straight line, path 1, they're near the outside, so they're going to be fairly short. If it chooses another path that goes near the center and then back out to B, there's going to be less dilation occur, so the ones near the center are going to be longer. So basically we want to measure the distance of each of those paths by counting up the meter sticks. Path 1, you count up 6 meter sticks, therefore it's 6 meters long. Path 2, there's 5 meter sticks. This is weird because path 2 is curved, yet it's shorter. This goes to show that at high speed, space-time becomes warped. Next, we're going to look at a wheel space station. This is an idea thought by Wernher von Braun back in the 1950s as a way to create sort of a gravity for astronauts if they were to live on a space station. The wheel would turn as the astronauts live on the outside, and from centripetal force, they would be anchored to the outside. As the wheel turned quicker, we could make this force of gravity go higher. Right? We need to spin at a certain rate so that would match Earth's gravity. As the speed of the wheel increases, it would feel like there'd be more gravity. We can write that down. The reason for gravity is so that astronauts won't get dystrophy, which is losing the ability to use their muscles. And this is something that we use every day here on Earth. Let's say this wheel approaches 99% the speed of light. So those people around the outside are going to feel a lot of gravity. If we look how time is affected, we know that as the velocity approaches the speed of light, time will dilate. It will slow down. We also know in this situation that if we look at force as velocity approaches the speed of light, the centripetal force, which is acting as the gravity, will also increase. Maybe there's some sort of a connection between time and between force. Here, more gravitational force means more dilation of time. This means that not only does speed cause changes in time, length and mass, but so does gravity, although a little bit differently. We're going to notice that as you go into a heavier gravitational environment, time also becomes warped because of that force of gravity. More gravity means more warping of time. This means on the surface of Earth, time ticks a little slower than it would somewhere up near the space station. So in summary, special relativity is the slowing of time due to speed. And in general relativity, this is the slowing of time due to gravity. Quite often, you might see on Discovery Channel or other resources the depiction of gravity on something called the fabric of space-time. The way we like to show gravity is it's like a trampoline, where if we put a massive object on the trampoline will become warped. We can show that here in this picture. This is like a sun in the fabric of space-time, and something that's very massive is going to create warps and dips in this fabric. So these warps and dips, this is what we use to simulate time dilation and length contraction, etc., due to gravity. The more warping that occurs, the more dilation happens. So massive objects warp the fabric of space-time. This is what gravity is. We'll look at some gravitational lensing in class.